Are people waiting? Okay, well, good morning. If you're on YouTube, we will start in a few moments. Luis, did we have a meeting ending now? Let's see the calendar, maybe, or finishing. Okay. I think we can start. And then people can join us. I'm gonna do a short introduction and then I will pass you the floor, okay? All right, welcome everyone. Good morning. Welcome to another talk of our webinar series. Today, we have the pleasure to have Robert Morgan from the University of Wisconsin-Madison. Robert is also a DES member, DES builder, and works with us in the transient and moving objects working group. And today he is going to talk to us about probing dark energy with gravitational lens supernova. Before we start, just a little reminder, this webinar is being streamed live on YouTube. You can watch it and other webinars in our YouTube webpage. Okay. So, Robert, thank you very much for accepting our invitation, and the floor is yours.
All right. Thank you, Rodrigo. Thank you for having me. This is exciting to be able to, this is one of the first times I've presented this project, and so it'll be fun to talk about. So first, I just want to introduce myself. As Rodrigo said, I'm graduating my PhD at University of Wisconsin in the coming months, so like April-ish. And it's a lot of work that has gone into presenting what I get to show you guys today. Fun fact about me that I like to start talks off with is that at one point during an observing shift at Cerro Tololo, I saw a lot of tarantulas, but not enough to actually beat the record for the observatory. And it was just an interesting situation to be in where I was hoping to see more tarantulas after being initially scared for the first one. But just getting into it, I want to first go ahead and thank a lot of people that have helped me along the way of this project. So everyone affiliated with the Dark Energy Survey and Fermilab, and then my two advisors on this project, Brian Nord and Keith Bechtel. So To get started with this, I want to return to the title slide that I had and basically just ask the question and analyze this image and say, what's that? Because I contend that it's just a really cool astronomical phenomena and is worth a much closer look that we'll take today. And so, first of all, we're looking at gravitational lensing. Definitely, if you've seen a lot of these lenses before, you recognize the characteristic features. But what you're seeing is a galaxy behind a foreground galaxy. And the gravitational potential of that foreground galaxy is deflecting the light from the background galaxy around it. And so you see these individual images of the background galaxy as opposed to just a single image. And this is a very rare phenomena overall. So because you have to have this chance occurrence happen of one galaxy lining up behind the other galaxy, and you also have to have powerful enough instruments to see galaxies that are very far away. We only see this in about one out of every 600,000 galaxies will have a strong lens. But in this picture, there's actually more. We're also looking at a supernova. And so this is the case where in the background galaxy, one of the stars has exploded, and its exploding light is reflected in the four images that you see. So it's not only the light of the background galaxy forming this ring, it's also light from the supernova entering into the image that you're seeing. And this is extremely rare. So first, you have not only two galaxies aligned and bright enough to detect, you also have to have a supernova go off in the background galaxy. And this is rare, like with a capital R, it's even more rare. And so every year you expect that this will only happen in one out of about 80 million galaxies. So it's a very rare phenomenon. It looks very cool. And it's definitely interesting for a lot of reasons that I'll get into today. And specifically, I want to talk about, here's the coolest part about what we're looking at. In this system that we have, when we have these four different images of the background galaxy, the light from the background galaxy travels different path lengths as it creates each of the four images of the background galaxy. So because all of these paths have different lengths and the speed of light is constant, what you observe, particularly when you have a supernova going off, is this explosion of its brightness getting really bright and then fading out happens in each of these images in sequence. And so you'll see the same explosion just at different points of time because of how it arrives to you. And in this field, we call this a time delay between the images. A very cool phenomena. However, I contend there's actually an even cooler part, and that's that if you can detect and measure this time delay, you're actually sensitive to cosmological parameters. And so this comes at a time, this figure is actually a little outdated now, and these error bars have gotten tighter and more distinct. But particularly on the value of H0, we see this tension. And this method is an independent way of measuring H0, as well as dark energy equation of state parameters. But the way it essentially works is the measured time delay that I have shown here is proportional to what we call the time delay distance and the gravitational potential of the lensing system. And so this time delay distance is a combination of three angular diameter distances to the lens, to the source, and then between the lens and the source galaxies. And each of these has a dependence on H0 and the omega matter, as well as the dark energy equation of state. So our goal here overall is to, once we can detect lots of these systems, we can measure the time delay and work towards having additional probes of H0 that help to resolve this ongoing tension in the field. So in principle, this can basically be performed with any time varying lensing system. It doesn't have to be a supernova. And in fact, the supernovae that have been used for this type of thing, there's actually only a couple. Like I think only one type 1a supernovae that has been lensed has been discovered, and only a handful of core collapse supernovae have been discovered. And that's because they're very rare. And so because supernovae have been historically rare in these situations, in these situations, a lot of these measurements have been performed with quasars in the background galaxies. And that's for a couple reasons. Quasars are generally brighter and they don't go away after exploding. So they're just there and you can continue, like you don't have to catch it while it's exploding. So that's why this field of, it's called time delay cosmography, has been somewhat dominated by gravitationally lensed quasars. And a cool couple images that we'll look into here. On the left, this is from DES work, and it's actually not just a quasar behind a foreground galaxy. This is actually a case where there's two foreground galaxies, and then a quasar in a third galaxy in the background. And so this is called double source plane lensing, leading to even more arcs and more images. So this was a very complicated modeling problem to attempt to figure out how the gravitational potential was affecting the time delays between the images. But overall, this one system produced a 3.9% measurement on the value of H naught. So it's really cool to see that come out of DES data. Across the field, there's also a collaboration that goes by the name of, that's one of my favorite names, called Holy Cow. And the HO part of that is spelled H naught. So that's what they're trying to do here. Again, just measure H naught. And they have performed imaging of several different gravitationally lensed quasars over the course of several years and have statistically combined their H naught measurements to get even tighter results. And that's another facet of this field where because each of these systems are completely independent, you can combine them, and as you detect more and more, you get tighter and tighter constraints on H naught. So that's how the kind of state of the field is for quasars. We're just constantly looking for gravitationally lensed quasars, measuring time delays, and inferring the value of H naught. But what I contend is that lens supernovae offer a lot of advantages over H naught, or over lensed quasars for measuring the value of H naught. And particularly that'll become increasingly better as we head into sort of the next era of optical astronomy fueled by the Rubin Observatory. So the first advantage that I want to talk about is that it's actually a lot cheaper to measure time delays from supernovae. So you are, picture yourself wanting to write a proposal, looking for these objects. Is a proposing committee going to be more happy to apply something or to give you time for something that takes a month or something that takes 10 years as shown on this plot? And I think lots of us from experience would lean towards the former there. And that's generally because AGN or quasars vary very small amounts. They don't vary as much or as dramatically as supernovae when you have a very large explosion. And so because of that small amount of variability, you have to characterize these light curves of AGN for like order 5 to 10 years to be able to precisely measure the time delays between these different A, B, C, D images, like the 4 images of the AGN. And so it's much more cost effective to look for supernovae. Another case is that supernovae light curves are very predictable. Because the variability in the brightness is always caused from the same mechanism of an explosion. And because supernovae have been very carefully observed for lots of programs, specifically supernova cosmology, there's lots of infrastructure of supernovae templates of existing supernovae. And you can kind of see here the difference in like how you would go about fitting AGN light curve on the left versus a supernova light curve on the right. To fit an AGN light curve, it requires all these observations over the course of 10 years. And then you have to perform a spline fit as opposed to what was going on the right, where you're actually fitting like mathematical equations, template models to your data, and you need much fewer observations. So because this predictability of supernova light curves really helps in their ability to be used in this analysis. And the final advantage that I think is the most interesting is that a particular subgroup of supernovae, which are the type 1a supernovae, commonly known as standard candles, have this standardizable brightness, where yes, based on general like color and other properties of the supernova, there will be this spread in how their brightness changes as a function of time. But if you account for color and then this other parameter called stretch that I can get into if people are interested, then you can make corrections to the observed luminosity and very tightly constrain the expected brightness of a type 1a supernova as a function of its distance. And this is very important for what we're doing here, because if you remember, the value of H naught depended on the measurement of the time delay and the modeling of the gravitational potential. And so if you have something that you know how bright it's supposed to be and it's being gravitationally lensed, what you'll do is you'll be observing like a magnified version of it based on the lensing. And you can infer how much that source is being magnified because you know how bright it's supposed to be at that distance. And if you know how much it's being magnified, that gives you information about the mass of the lens. So it really removes a free parameter in the fitting of the overall system. And so it's overall much tighter on your constrained value of H naught. So these are three important reasons why supernovae are just great candidates for time delay measurements. And then there are a couple drawbacks that I sort of mentioned earlier, and those are that supernovae explode and then they go away. And then they're gone and you can't see them anymore. While AGN have the benefit of being there constantly and just varying over long periods of time. And so if you only have a few nights of observations, you don't have to get lucky to detect a gravitationally lensed supernova. And then on average, AGN are much brighter than supernovae, which is why there's a lot more AGN in lensing samples than we see supernovae today. And so this brings back to the question that I sort of posed as we were going through the more introductory slides, that aren't these things like, why do you care about looking for gravitationally lensed supernovae? If like, even if they have benefits, weren't they rare with a capital R? And then we say yes. There are really every year approximately one gravitationally lensed supernovae for every 80 million galaxies. So it's really a tough problem in terms of how frequent these things are. But if you are looking for something that's 1 in 80 million galaxies, one strategy is to just observe billions and billions of galaxies. And that's exactly what's going to happen over the next 10 years of astronomy, where in the Southern Hemisphere, the Vera Rubin Observatory will start observing. And over 10 years, we'll get detailed characterizations every 10-ish nights in 6 colors of approximately 17 billion galaxies starting late 2022. So when you're observing 17 billion galaxies, the odds of detecting something that's 1 in every 80 million galaxies become much more in your favor. And so if you work that math out, over the 10-year survey of the Rubin Observatory, we're looking for about 2,000 gravitationally lensed supernovae. And so this generally becomes the needle in the haystack problem, where we have lots of these things that we have a few of these things that we're looking for, but they're in a data set of 37 billion objects. And what we need are automated detection strategies to try to find them, to be able to do make cosmological measurements, do time delay cosmography, and constrain the value of H naught. So 2 detection strategies that have been proposed so far are very, very creative, and but they do both have their drawbacks. And so I'll start with this one on the left, which I'll refer to as a strong lens watch list, which is after the first year of an astronomical survey, you'll generally be able to identify where all the systems with strong lensing are in your data, and then you just monitor those systems over the remainder of your survey and essentially wait for a supernova to be in a galaxy that's behind it. And this works pretty well. However, there's the drawback that if the background galaxy is too faint to detect in just 1 year of data, then your strongly lensed system won't be in your watch list, and you will miss any transients that happen in that system. And so a calculation was done for the Rubin Observatory, and it was found that you can miss anywhere between 10 to 40% of strong lenses and strongly lensed transients if you do this method. So it's a big range, but it's still a lot of that is still a lot of gravitationally lensed supernovae to be missing out on. Another one specific to type 1a supernovae, which again are important, remember, because of their standardizable brightness, helping to model the gravitational potential, is to basically look for type 1a supernovae that are just too bright for where they are in distance. And that would mean that there would have to be some amount of magnification. And this was proposed to basically look at elliptical galaxies, because in elliptical galaxies, you have very little core collapse, very few core collapse supernovae. So you'd be pretty confident that any supernova that goes off is a type 1a. And to look for galaxy or supernovae above a magnitude threshold, and here they suggest an absolute magnitude cut of -20. And that rules out all foreground supernovae, so you're only seeing background gravitationally lensed type 1a. And this is, I think, a very creative method. It has the feature that it relies on looking for an elliptical galaxy. And it also has the feature that you have to observe the supernovae somewhat close to peak brightness, or have enough epochs before and after the explosion, the peak, to be able to fit it and determine what the peak brightness is, to convince yourself that it's actually too bright to be just a foreground supernova. And so this also has the potential to miss out on quite a few supernovae. And so that's generally what's been done so far in terms of how people plan to look for these objects in the next era of astronomy. And so next I'm going to talk about our approach to this problem, because it's quite different. But before we do that, since we've covered a lot of background, I just want to pause and ask if anyone has any questions. Been told to wait approximately 30 seconds, just in case. Okay, great. So we'll keep going. And now we want to think about, we have this problem of very rare objects that appear in images as strong lenses and are time varying. And we want to think about what aspects of those systems we can use to exploit, really, to try to detect these as best as possible. And so that's exactly how we're going to approach this, sort of with two prongs, because there's two parts to this problem. One is that in an image, you can look at this image with your eyes and say that's strong lensing going on. And so that means there's information being carried in the image of what you're looking for. So there's image-based features that we're looking at. And then there's also the fact that there's a time varying aspect. And if you want to get really into it, it's that there's time varying, and that the time varying is the same signal, just delayed. But let's start with the images. So we're going to start with the images and think about how to go about detecting strong lensing in an astronomical image. And luckily that's been done before by lots of different teams. So there's a couple different approaches. When it started off, this field was generally just like scan with human eyes a lot of images and look for blue rings around red objects, and then you'd convince yourself. After seeing a lot of these, you'd say those are strong lenses. And people in DES made huge catalogs of this. So Tom Deal was a leader in that. And then as data sets got bigger, you needed a more advanced detection strategy, because humans didn't have the time to go over lots and lots of images. And while a paper did get put on the archive last night of people going through by eye and looking at all 5,000 square degrees of DES data for strong lenses, going into the Rubin era, that when the data set's even bigger, I don't think that's going to be as feasible of a method. And so the general approach has been to default to machine learning. And when you're looking for features in images, this problem has been tackled by a technique called convolutional neural networks. And without getting too much into the weeds, effectively what these convolutional neural networks do is inside these convolutional layers here, or you can think of this, the whole box as the image itself, and this smaller box as these matrix operators. And these matrix operators are applied to the image, and then basically matrix multiplication happens, and you carry that through with lots of different of these matrix operators, or kernels as they're called. And as the neural network learns, it basically uses its existing kernels to make a prediction of the images. And then it asks itself, is my prediction correct? And if it is, then the weights in these matrix operators kind of stay the same. But if you're wrong, then they get an update. And so this is how the neural network learns. It updates these weights in these matrices such that it ends up finding the shapes in the images that are most characteristic of the true identity of the object in the image. And so this has been done in several large survey data sets. DES, this was done in 2019 by Colin Jacobs, and he found approximately 500 strong lenses in the dark energy survey, confirming what Tom Deal had done for a number of lenses, and found there was a lot of overlap, but also found a lot of new lenses. And so generally going forward, this is kind of considered more or less a solved problem. Similar things happen with light curves. And again, the traditional way of classifying supernovae, as I showed above, you can actually fit supernova data to templates, and that would give you, is it more likely a type 1a supernova or a core collapse supernova or not a supernova? But in the larger field, when template fitting becomes computationally expensive, people have also turned to neural networks, and just a different type of neural network. So instead of a convolutional neural network acting on images, this would be a recurrent neural network that operates on time sequences of data. And shown on the right here is kind of like how, as a function of more data becoming available, a technique like this is able to distinguish between a type 1a supernova and a core collapse supernova. And so it's analyzing the sequence of the observations with knowledge about the time points. And this is a technique that's actually used for any type of sequence data. So oftentimes natural language processing, like speech analysis, is done using techniques like this. And the way this network works is each point in the data set is put in. So like this is point 1, point 2, point 3, point 4. Oops, sorry. And point 1 is put into this block, point 2 is put into this block, point 3 is put into this block. There's operations that happen internally, like in the convolutional neural network, that are geared towards understanding how the sequence changes. And then it kind of perpetuates that into another layer of these shown here until it figures out what the defining characteristics of the sequence are. And so Anais Moeller, shown with a figure from her paper here, is used this technique to build one of the most accurate supernova classifiers to date. And this is going to be used in dark energy survey supernova analysis for their photometric samples. So they're going to be able to do cosmology on all the 3,000-ish supernovae found in DES, not in the deep fields that haven't been spectroscopically confirmed as a type 1a supernova, because they've developed technology like this to photometrically classify them based on their light curve properties. And so we have basically these two deep learning techniques, convolutional neural networks that are good for image-based features, and recurrent neural networks that are good for looking at sequences. And what we've done in our approach is we've actually combined them into one neural network. And this is a somewhat of a novel architecture in the deep learning community, but it's generally based off of, this is one of the first applications where I would contend that image-based features and time-based features are equally important. And so what we do here is we have sort of the convolutional layers that I mentioned before, where you have matrix operations being applied to the images. And then after a couple layers of that going on, we flatten it down into just an array of numbers. And then on the light curve side, we pass the light curves through blocks like these. where they're learning the features of the sequence. And then after they've learned the identifying qualities of the sequence of the time varying brightnesses of these detected systems, you again flatten them into an array, concatenate these two arrays. So then you have both the features of the images and the features of the light curves, knowledge of both, and then allow the neural network to classify them and weight them appropriately without having to sort of infer as a human what aspects are more important, the images of or the light curves. Let the deep learning architecture kind of find the optimal weighting for you. And so this, we refer to it as like a multi-input network. The name we're giving it is called the zipper network because you're kind of zipping these two things together and then making classifications later on. But what we find is that this is actually a very powerful technique, particularly for finding these systems. And so as a first test of this, we've made a lot of simulations of things that you might see in the night sky, thinking about going forward and applying this tool to astronomical survey data sets. And so we break this classification problem down into 4 different categories. One, sort of the largest category here, of just anything you could see in the night sky that is not lensing and not a lens supernova. And so you see just galaxies by themselves, you see galaxies near each other, you see stars near galaxies, you even see supernovae in a galaxy. And then you have empty sky that's just picked up by your image detection strategy. And so we've simulated both the images and extracted time varying behavior from a sequence of images. And that's shown here in these normalized light curves. And then the other systems we have are anything that has lensing. So you have anytime there's lensing, and then there's also maybe a star involved or another galaxy that's just nearby and not involved in the lensing, but all systems that somewhat display aspects of lensing. And then we have 2 lens supernovae categories, one for core collapse supernovae and one for type 1a supernovae. And so this is going to allow us to not only look for lens supernovae, but also look for, in particular, type 1a supernovae and see if we can actually identify the supernovae that are going to be the most useful for H-naught measurements. And the software we used for this, since I worked on it with similar people, I'll just do a quick I guess shameless plug, but what we do here is we've developed a way to capture the properties of an entire data set into one text file and also build in the observation properties of real astronomical surveys. So these simulations use DES data to, and like the observing conditions of DES data to build into the images in the simulations, and then we get DES quality data out. And then we've also done it for Rubin Observatory expected data. And so we're able to make this whole data set of all these different astronomical systems, all with one piece of software, and go forward and then try to train a deep learning architecture on the data. If you're interested in doing strong lens simulations in large data sets, I'd be happy to chat via email if this is something you'd be interested in. But we can go and see how well this approach actually works. And what we're seeing here they're called confusion matrices. On the horizontal axis, you have the class that the zipper network is predicting. And on the vertical axis, you see the true identity of the class. And so this is in an independent test data set. And what we see is generally a large dominance by the main diagonal in these plots. And that's indication that it's working well and it's able to learn what these systems are and identify them. And then there's also more information we can pull out of these plots. And so if we think about what characterizes the DES deep fields or the supernova fields and the general LSST Rubin Observatory wide survey, there's a couple differences. One is the cadence of the survey. So the DES deep fields were imaged approximately once every 6 nights, whereas the Rubin Observatory will be closer to every 12 nights, maybe every 13 nights for the same spot in the sky. And so there's much better time resolution in the DES deep fields than there are for the main survey of the Rubin Observatory. But big difference is that in the DES deep fields, when they were planning the survey, they were okay with lower than average seeing conditions in the supernova fields. And that's because the software they were using to detect supernovae was actually able to detect varying supernova in poor seeing conditions. And so anytime there was a night with poor seeing, they just said, all right, let's go do the supernova fields. And then when there was better seeing, they did the DES wide survey to do weak lensing analyses where you need really good seeing. So just to summarize those two differences, DES deep fields had worse seeing than LSST wide, but the LSST wide field had a worse cadence than the DES deep fields. And so what we find is actually something kind of interesting in that the image-based features that are like the resolution of the lens that come from having good quality seeing is more important than a high density cadence. And so this kind of tells us that if you're using this technique, you can plan out and sort of optimize the detection strategy for gravitationally lensed supernovae, because you don't need to have very finely spaced nights to observe. You can actually get away with one every couple weeks. And as long as you have high quality seeing, you'll be able to detect these objects. So that was good to see that in this four-way classification problem, we can detect what's a lens, what's not a lens, and then what is a lens supernova, and also have somewhat low confusion, especially in the better seeing conditions of type 1a versus core collapse supernovae. But also a general application of this is to say, let's just try to find lens supernovae, because in general, any lens supernova can help you measure H0. And so that would be taking this confusion matrix and thinking about it in 4 quadrants instead of 16 different spots. And so this bottom right would be predicted lens supernova and true lens supernova. And then this would be predicted not lens supernova, but it actually is a lens supernova. You can see the other two there. And so because most of the confusion that you see in this confusion matrix happens in spots adjacent right off the main diagonal, that means it's still pretty good at saying what's a lens supernova and what's not a lens supernova, and you have very low representation over here. So if we map this 4-way classification problem down to a 2-way classification problem, we can basically have a common sort of metric in machine learning analyses called a receiver operating characteristic curve, or a ROC curve, and effectively measure how good of a lens supernova detector this approach is. And there's a couple other data sets that I used in the paper that are present on this plot that I didn't show confusion matrices for, but the LSST-wide data set and the DES deep data set are still here. And what you can see is that, and the way to read this plot is the area under this curve is closer to 1 you are, and the closer you can get the curve to be like a right angle going up to 1 and over, means the better you are at detecting supernovae, or detecting what you want to detect. And so in the case of detecting lens supernovae, we get a very high area under curve for the LSST wide and a comparably high, but not as good for the DES deep fields. And so this tells us that, as a general lens supernovae finder, this technique actually works extremely well. And it's exciting going forward to have something like this in the upcoming Rubin Observatory era.
What is this DASI DOT?
It's an optical imaging survey that's built to go along with DESI, called the DESI Detection of Transients. Yeah, it's like, yeah.
Okay.
And yeah. So it's actually just a proposed survey that's going on right now. It's about 100 square degrees in the, I'm not sure if, I think it's in the Southern Hemisphere, but it's being observed every 3 nights in 3 bands. And so it's
it's an extension of the accounts. It's not the original.
Yeah.
Okay. Now, one thing I didn't understand about the cadence, I thought the LSST would have a 3-day cadence.
It's 3-day cadence to visit the same field, but about 10 days to visit it in the same band.
So it's a band. Okay, yeah, okay, I got it. All right.
But yeah, those are things I had to think about a lot when designing these simulations.
Yeah, you need, yeah, because you need the color information separately. That's okay, I got it.
Okay, and then the final result that I think is the coolest out of this technique is we were able to look at how many observing epochs past the first detection each of our light curves were, and what the probability of and what the network was classifying the objects of as a function of that time. And so what we see is generally, this is the true positive rate. So if something is a gravitationally lensed supernova, what fraction of the time is it classified a gravitationally lensed supernova? And so for all supernovae together, thinking about this as just a lensed supernova identifier, even one epoch after the first detection of the supernova, so this is, you have two observing epochs basically, right before the supernova peaks, you're able to get about 80% of the time, just say this is a gravitational lensed supernova. So if you only need two epochs to detect it, or to have a good idea of what you're looking at, that's really good for triggering spectroscopic instruments to say, let's get redshifts for these, let's confirm that it's gravitational lensing, and let's confirm what type of supernova it is. So this fast, rapid detection abilities of this technique that we're seeing is really promising for follow-up instruments in the Rubin Observatory era. And you can see that it's also generally good at doing it just like, is it a type 1a or is it a core collapse supernovae altogether? But it is best as just a general lens supernova finder, because there will always be this tiny confusion between lens supernova or core collapse supernovae and type 1a supernovae. So that's essentially where we're at right now in this project. Looking forward, just to sort of, I guess, to summarize first, but what we've done here is developed a novel approach to finding gravitational lens supernovae. And we want to find them because they're excellent probes of H0, and they'll be in very high numbers during the Rubin Observatory era. We have a paper that's well through the DES review process that'll be on the archive soon. And we're planning on doing a full search of the DES deep fields. So not just using DES data to inform our simulations, but also just on the raw DES data, looking through these deep fields, try to find, there's an expectation value of 1.5 gravitationally lensed supernovae. So we're optimistic that we might be able to find the one that's hiding there. And so hopefully I'll have an update on that for you guys at some point in the future. But I just wanted to thank you again for having me and answer any questions.
Okay, thank you very much, Robert, for this amazing talk. We have now time for questions. If you joined us on YouTube, you can put your question in the comment section.
I was trying to find the hand. It took me a while.
Okay, go ahead.
I do have a question. How scalable this is for LSSC? Because you have to work both with the images and actually grab light curves. I mean, do you have? I mean, it sounds like a big software engineering problem.
I left this out because I felt like it was a little too in the weeds. But the way we do it, when you have strong lensing going on, it's actually very difficult to extract a light curve using things like source extractor because of all the blending issues. And if you don't have that good resolution, sometimes the two images of the light curves are on top of each other. So we've actually developed a different extraction strategy for this problem, where you just have a time series of images. And on each image, you use a very wide aperture and just measure all the raw pixel values in that aperture. And you subtract off the background value as well. But then you just track that pixel, that sum of all the pixel values. And you do that for each image. And then that's your effective measurement for the light curve. And then once you have the light curves pulled out of the images with just this sort of cheap aperture mask that you apply to the images, you co-add all the images. So you have effectively one image in each band and one number for each point in time in each band. And it's done without applying any sort of like light curve extraction programs that would be computationally expensive to run. So we solve.
But still, I mean, a lot of images to process. I mean, how you envision doing that? I mean, as part of DM or for LSST, I mean, or you're going to set up a special system to do that?
LSST plans on having lots of those systems available to people. So hopefully that's already a solved problem, and there's people above my pay grade working on that. It is a lot of data, and it will be a challenge. But I think the survey is generally prepared for that. I mean, they have things set up to like detect new transients in every objects and expect to issue, or in every image, and expect to issue like 10 million transient alerts every night.
So will that be done as part of the regular procedures or something separate?
That part would be part of standard LSST procedures. What I'm proposing here is sort of just like
a plugin.
What I would do, yeah. So
okay.
When images become available, that's something we could do this on. Yeah.
Okay, very challenging. Congratulations.
We have a question from Clasio now. Clasio, go ahead.
Hi, Rob. Hi, everyone, and thanks for the nice talk. Yeah, my question is maybe part of Luis' question. Is actually, I assume that you're not planning to put through the network the full imaging of LSST, right? So how you plan to do that? How do you plan to select these targets, right?
You would start mainly looking at where galaxies are detected. And then you could trim down your galaxy sample if you want to sort of more nearby larger galaxies that are more likely to be lenses. And so you can sort of start there, and then if you don't find anything, keep going.
Yeah, but I mean, billions of galaxies, right? It's also a huge number.
Yeah. And you have to, I'm not planning on doing this on my laptop, if that's what you're getting.
Okay. Okay. Oh, thanks.
Thank you, Clasio. More questions? Well, I have a question. Maybe it wasn't clear for me. Did your training data was simulated data or was
What I'm showing here is all simulated data, but the simulations have the characteristics of like the real observing strategies of us. And like we queried the catalogs to get like the seeing and the cadence, and the images, the objects simulated are from DES catalogs as well. So it's like the morphology, the redshifts, the color, it's all from DES data.
Also, you talked about false positives. Did you have any idea of having false negatives?
That's something we haven't looked into that much yet. Generally, though, the false negatives come from low mass lensing galaxies or very faint supernovae. So just generally things that are hard to detect. Or if it's in the case of a low mass lensing galaxy, you just have like smaller amounts of lensing, like less like magnificent arcs to find. And so it's harder for a network to detect that there's actually a lens going on there. So generally false negatives in this technique are going to be the same types of false negatives that come out of astronomical searches and existing Malmquist bias and stuff like that.
Yeah. Well, thanks. We still have time for more questions. While we wait, I have another very basic question. What is the time scale of the supernova event? Does it
About a month.
changes a lot?
Yeah.
Months, okay.
Weeks to months, yeah.
But never below that?
No.
Okay. Okay. If there are no more questions, we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. And for the next week's webinar, we will have Hector Hilmarin. He's from Universidad de Barcelona, and he will be talking about large-scale structure tools for the new generation of surveys. Thank you everyone for attending, and a special thanks to Robert. Thank you, Robert.
Thanks, everyone.
Okay. Everyone have a great day, stay safe, and I hope to see you all again next week. Bye-bye.